Okay, so today's topic is non-bonded interactions or non-bonded potentials. So in non-bonded potentials is basically when we have two atoms that are not bonded with any not bonded with any bonds, which means they are just interacting with each other based on charges or based on dispersion forces. So now let's classify them a bit. So if you have two particles that are charged, then the theory that we apply is Coulomb potential or Coulomb interactions. So what does Coulomb interaction say? That any if two atoms are interacting with each other using some charges, their potential will depend on the multiplication of the two charges divided by the distance between them. So that will be the equation to directly explain how two atoms of how two charged atoms interact with each other. So what does it look like basically? This is the equation where 1 by 4 pi epsilon naught and epsilon r, this whole thing will amount to a value because here epsilon r is the epsilon of the medium that experiment is happening. So in your case it will be water, so there's a value for that. And then epsilon naught is the epsilon of the vacuum. So you basically get a big I mean not big, you basically get a um, static value, right, for this part. So you are left with just q1 q2 by r. So what does this part looks like if you plot this q1 q2 by r, and if you just forget that there is a constant in front of it. So if you have a repulsive regime, if you are in the repulsive regime, which means um, that you have similar charges, right? Either negative negative or you have positive positive. In that case, the curve looks like this. And if you have opposite charges, which means plus minus or minus plus, then you have a plot like this. Now, this is pretty easy. We all have read this in probably our under 10 standards in our schools. So now is the second part, which is Lennard-Jones interaction, which basically describes how two atoms interact with each other in a non-charged environment. Um, an example for this is van der Waals forces, right? So these kind of forces, which are short range, non-charged interactions, these are very weak interactions, and those are described with Lennard-Jones potentials. And what is Lennard-Jones potential? Lennard-Jones potential have two components. First is repulsive part, and the other one is the attractive part. Now, why are we choosing Lennard-Jones? Because this is very computation friendly. What do I mean by computation friendly is that calculating these values is pretty easy. So the computer only needs to find, this attractive part, whatever this computes to, they just need to find that part. And what will they do is that they will put a like square on the whole thing, and you will get this c to the power 12 term. So basically calculating that is just one step away from this part, and that's why people often choose C12 and C6 version and not any other version. For example, there are C9 C sorry I mean you know so there's a term for this. They call it 612 potential, which means attractive part is to the power 6, repulsive part is to the power 12. But there are versions where there is something like 6 9 potential, or there are other versions which I'll just show you in a moment. So the graph looks pretty similar as you might have seen, right? It's an similar to an anharmonic plot. But what happens is that this repulsive part, 1 by r to the power 12, that's this part, which is very steep and upward going, right? So it means that whenever there's an atom which is, let's say, close to 0.5 nanometers or 5 angstroms, it's in the minima. But when we are taking it closer, we will like find the energy is going pretty high, which means the more steeper it is, it feels like a wall. So if there is an atom that cannot cross this part because after it crosses that, the potential increases a lot. So it feels like a wall for the atoms. So that's not exactly how these weak interactions work, right? Weak interactions are like they should be soft in nature, at least in the around the minima. They should not be that steep. So that's why there is this person Buckingham who have introduced this new potential, which is the Buckingham potential. But the problem with this is that computing this is much more computationally expensive than the Lennard-Jones potential, as I said, because this repulsive part is just a square of the attractive part, so it's very easy to calculate. But here, nothing like that works, so they have to actually compute this exponential term separately, which means you are wasting more computational time. And why is this so important? Because let's say you have 100,000 atoms. So the permutation combination, and let's say you have a small box, let's say 10 Armstrongs by 10 Armstrongs, right? And everything is just water. Now just imagine with me for a box like that, sorry, not 10 Armstrong, but 10 nanometers by 10 nanometers, something of this. Let's think about it. And when you are working with non-bonded potentials, think that if there is one atom here, or let me just draw it, right? I think it will be then much more easier. Let's say we have a few atoms here, right? Okay. Sorry for that. Let's say we have four atoms, right? And we want to find the like we are computing some non-bonded potentials. So what will happen? We will take this as a center and we will compute, distances between them. So they just for four atoms, there are about combination comes to about three, and then you also forgetting this, and you're also forgetting that. So for four atoms, it comes to about one, two, three, four, five. Five interactions you need to compute, right? If you take this to, let's say, 100,000 atoms, you can do the math for yourself. It's, exponentially growing. So I think there is also a term, there is also a mathematical calculation somebody has done, which states with how many number of atoms increasing, how much more computation you have to do, and that's basically exponential. I'll show you that curve after in the next video, I would say. So now you get an idea that how much important it is to keep the non-bonded potentials compute friendly, so that we can compute more and more potentials, right? And at least the speed would be much higher for that. So that's the only reason why we not use Buckingham potentials. But despite that, Buckingham potentials give you more realistic repulsive term, which we actually want. Um, and apart from that, I think we have covered everything in this series. So yeah, see you in the next part. We will summarize the whole force field thing once, and then we will move to how to run, like how do atoms move, right? So far we are talking about if there are two atoms, how they should interact with each other, what is the kind of forces they will exhibit on that. But the next part will be how do atoms really move from one place to the other, right? Because in simulation, that's the whole construct that we need to find. Okay, so have a nice day. Bye bye.